Jagamoy completed his undergraduate studies at Presidency College, Kolkata, India 2010, and pursued his master's degree in applied geology at the Indian Institute of Technology, Bombay, India 2012. Later, he worked as a well-said geologist and micropaleontologist for the Oil and Natural Gas Corporation Limited, ONGC, for 4 years. Jagamoy joined UJ as a PhD student in April 2016 and is working with Professor Axel Hoffman on the 3.5-GAU-old Archean rock record of the Singbom Curtain, India. Jagamoy is interested in the Archean sedimentological and geobiological processes that include a detailed investigation of volcano sedimentary successions. His research is aimed at understanding the evolution of early Earth and the emergence of life through a combination of field, petrographic, and stable isotope studies, C and O and S. Jagamoy is currently in his final year of PhD and is responsible for the confocal laser Raman spectroscopy lab at the UJ.
Good morning. Thank you, David, for this lovely opportunity. I am Jagamoy Jodder, a postdoctoral fellow at the Evolutionary Studies Institute, University of the Witwatersrand in South Africa. I am conducting research on evolutionary process, largely focusing on ideas related to cooperation behavior in the earliest microbial fauna from Earth. And the discussion of today would be how our early Earth was and why we should be interested to study the early Earth. So during my PhD, I conducted research mostly on early Earth conditions. It was mostly from the Indian subcontinent. I studied ancient rocks that are of age of 3.5 billion years. And we will discuss more about that time period of this age of 3.5 billion years, which is roughly known as Archean. And we will go on discussing about the Archean period from Earth's history and what is the Archean and why we are here today to discuss the Archean Earth. So the beginning of our talk would be mostly focusing on the Archean Earth history and with the Archean Earth, how life evolved and what consequences did it have on us today, as in when we see modern human beings or any animal species in our Earth, what do we find and how did our Archean early Earth shape our modern Earth and how dynamic was it to shape what we are as an existence today. So with that, I would share with you all a slide presentation to show you few snapshots of the Archean Earth history.
Why studying the early Earth?
It's a very interesting question, and the aspect of it is that on our modern Earth, when we are with all these events of COVID and pandemics, and we are far away from the Earth that was in the distant past, and we have Earth when it was the early Earth, it looked like something more similar to this. This time period that is known to the geological fraternity or the fraternity of science is known as Hadean. So this time period of Hadean is very important because it captures the most unusual settings that is of its kind, different, because as you can see, the Earth was covered with volcanoes, there were eruptions, there were meteorite impacts, and very close to meteorite impact, we have a very well-known meteorite impact in the Yucatan Peninsula of Mexico, which is known as Chicxulub. Now, imagine having Chicxulub everywhere, mostly on Earth, and then volcanic eruptions, and these conditions were hellish. That's where this name is derived from a Greek word called Hade, which means Hadean Earth. But you may wonder why should we bring this Hadean Earth conditions to our present day Earth and then discuss in the context of when we can have our Earth where we are all alive, we are all happy, and not under this Hadean Earth conditions. But actually, this is how we all started, and we, in a way, I encompass our Mother Earth when we talk about we, because Mother Earth and life co-evolved. And when I say co-evolve, we will discuss how the co-evolution took place. And with this, we will kick off by saying that the first phase of Earth was very, very rough, and the conditions were probably like hellish. But when we go to our beautiful Mexico City and our modern day city of Mexico, this is a skyline view of Mexico. And then you would want to go and jump to some of the streets to have some nice um, time around in Mexico. And the first important thing that we would want to have is to breathe. And this thing of breathing is easy for us now to conceive or to have this idea, because the present day atmosphere is with 21 percentage of oxygen. And when I say oxygen, it's free oxygen, meaning that the oxygen is available in free O2 state in the atmosphere. But was it like this in the Archean or in the Hadean time? It was not. And that's how we are lucky. So now we are very fortunate to have this oxygen, to breathe in oxygen, and then to respire carbon dioxide, which is of no use to humanity in all likelihood. But we are all using the most essential gas, which is oxygen.
How can our ancient Earth give answers to understand our modern Earth?
So now when we talk about our present Earth and the Earth that we are living now, we are somewhere here at the top of this column, and this is the time period. So this is our stellar evolution of our solar system and the Earth in itself. So where we have nebular processes, collapse and accretion and differentiation right at the beginning of our solar system. And then this is the time period which we will discuss today. So the time period from Hadean to Archean will be touched upon roughly. And when we talk about what our past or our early Earth was, so we are talking about something here when we want to dig down deeper and see where we would be in our Earth's history. We would be here. And this is where the solar system started close to 4.5 billion years ago. And now humanity, we stand somewhere here. So if we have to take a deep dive down into the spiral of our Earth's history, we would be going somewhere deep and going further deep down, pointing somewhere here. So the distant past is very, very, very far away. But we will see some of the evidence and how our past provides us some answers for our modern our evolution and us as an existence. So when we talk about the Archean and the part that it was very different from the Hadean Earth also, because the Archean was slightly much younger to the Hadean Earth. Well, there were also meteorite impacts that showered on our Earth then, and the moon was much closer, so the tidal impacts were different. But the very important aspect is that the oxygen concentration was 0.001% in the atmosphere. So which is of very low abundance, right? And one cannot actually do anything with that.
How complex life on modern Earth co-evolved with Earth itself?
So I will start with the fact that how the Archean Earth was. The conditions were roughly like where you were having meteorite impacts, and the moon, as I've mentioned, was much closer, but then there were also volcanic eruptions covering all across our Earth. So there were these huge eruptions that led to emissions of volcanic gases that were toxic in nature. And then there was a strong absence of ozone, and this resulted in the impact of ultraviolet radiations more frequent into our Earth's atmosphere. And the other important aspect is that the Earth was covered by some primitive oceans, which was the first primary requirement for life to be existent. Now, when we talk about this, but it's very difficult to understand the Earth's history because it's in terms very patchy. And I try to imagine it as a photograph of Mona Lisa, and I compare our young Earth or our early Earth as a Mona Lisa's portrait. But then let's say this Mona Lisa's portrait is compared to an old Earth, and this elderly Mona Lisa is now in a photograph which has now been crumpled or broken in some parts. So would we be able to catch the very details that one could have encountered in the primary photograph? It becomes very difficult to see these aspects from a very old portrait itself of Mona Lisa. So it's also a challenge to reconstruct the Earth's history because the ancient history of Earth is not captured everywhere, and we do not have many places where we see the rock record preserved because the Earth is very dynamic and it does many activities within itself. It's a beauty in itself, so it does not preserve many things, but you will have to go and dig down and do more research to unravel some histories. Talking about life and how life evolved with these conditions around, and from the patchy record that we know of our Earth, of our ancient Earth, it's always a mission because it's a mission like you have to go and look for a needle in a haystack, and it's always never easy because it's a very difficult task.
What are time windows?
So talking about the earliest uh, rock record and what and where we should go to find them comes in the aspect of different places on Earth where these rocks are preserved. So the different places are South Africa, India, and Australia. When we go there, we would go to have this vision to find for some time windows. And these time windows are referring here to the Archean Earth windows, where we find very well preserved rocks only in these places that has been reported so far. And when I talk about rocks, so there are some of the rocks that I have to show you. So this is one very specific rock. It's known as komatiite. You can see some needle-shaped features. These are all made up of some mineral which formed at that time when this lava erupted on the surface of the Earth. And this eruption of lava took place close to about or even higher than 1600 degrees Celsius. So you can imagine how hot the Earth must have been then. So it's a very unique rock, and it's never easy to find this everywhere. And also on our modern Earth, we don't have temperatures as high as 1600 degrees. So we do not form this kind of magmas in our modern Earth. But it was very prevalent during the Archean times, and that was one of its very special rock type. So it's mostly made up of olivine, which is magnesium iron silicate, and there will be more rocks that will be shown throughout the presentation.
Why are South Africa, India, and Australia important for time windows?
Once you go to South Africa, India, and Australia, these photographs that I show you here are all microbially induced structures. And this means that when you go to visit these places on Earth, you will come across these domical shaped structures. And these are nothing else than microbial communities occupying the shallower level of the ocean. And with that, they trap the sediments and then they bind the sediments. They have their microbial activities. They use the sunlight's energy, and then they created these structures which were domical in nature. And these are also some examples from India, Australia. These are some conical stromatolites. So here, if you go to all the Archean rock record of Australia and South Africa and India, if you are lucky and if you happen to visit these places, you will come across these structures which are made by microbes in the past. And if you were to see these structures on our modern Earth and how cyanobacteria right now provide this kind of structures. These are modern day replicas, which are stromatolites, and they are preserved in this oceanic water column of the Shark Bay area in Western Australia. So if you are close to the Shark Bay area in Western Australia, you can see modern bacteria creating these domical structures, and then you can connect to the past, because these were the same type of organisms that lived during the Archean and the oceans, on the shallower level of the oceans. They undertook photosynthesis, and they created this kind of organosedimentary structures.
Microfossils. What do we know about them and their contribution to evolution and the increasing amount of oxygen of the planet?
Other than that, what we do have is that from both, not both, but all the three places that I've mentioned, you have microfossils, and they are very tiny organisms. They are very, very tiny. When I say tiny, it means our hair follicles are, if I'm not wrong, they are 70 microns in diameter, but these are 20 microns. So you can imagine how tiny they are. You have to look them under the microscope, and the only rock type that is known to preserve this are cherts. So this is an example of a chert. This is mostly made up of silica, and the black part is made up of silica plus carbonaceous matter, mostly carbon and some organic material. So what you do have in this is, if you cut the rock, make a slice of it, and then see that slice under a thin section, under a petrographic microscope with that thin section slice, you will come across these features. And these are the earliest microbes, which are as old as 2.51 billion years. The other ones that I'm presenting here today in this talk are 3.4 billion years. You can see how the shape of these microfossils are. They are spheroidal, and sometimes they have a tail-like flared out appendage. They sometimes make up colonies. One of this is linked to the other, and then this is linked to the other in a chain type of morphology. And this was recently studied by different scientists, where they show binary fission of process of reproduction. So these are unique microfossils, and all made up of carbonaceous matter, and they are linked to one another by a flared out appendage, or like a tail-like feature towards their extremities. So these are very unique microbes that existed during the Archean Earth. So therefore, the other aspect of our time window was that we have slightly seen the Archean Earth, the Hadean Earth firstly, which was hellish, with mostly not much of rocks to study. But the Archean Earth, where we can go and visit places from South Africa, Australia, and India, we can see rocks that do preserve activity from microbes. And then they created these features. You will go and see them in the rocks itself, because these are megascopic, meaning you can see them from your naked eye. You can see them when you'll be outdoors in these places. You will find these domical features. These are all examples of domical stromatolites, made up mostly by cyanobacteria. And then there were also microfossils, which have shown to form colony type of assemblages, one linked to the other. And why it is important? It is very important because we discussed in the beginning that the oxygen that we are so luckily or happily breathing today did not come overnight. It happened through revolution in biological processes that took place over a billion years of history. And roughly from 4.5, when the solar system started, but then we have rocks on Earth which are close to 4 billion years old. We did not have oxygen, but close to about 2.46 to 2.3 billion years, we now have 1.5% of oxygen. And this oxygen from the shallower part of the oceans now went up to the atmosphere. So now here we are here in the present day oxygen levels, and you can see how high it is. It is a log scale, and then you can see how the concentration of oxygen is. It's 21% in the atmosphere. But the first very baby production of oxygen started off in the atmosphere with 1.5, and this is a big jump from now what we see and from then what it was. So as a humanity, we have evolved because of the evolution of our Mother Earth, right from 4 billion years to 2.5 during the Archaean history, and that what has evolved the conditions for many complex organisms that happened close to 1.7 billion years. And then we have eukaryotes, and then we have more complex organisms, and us as human beings somewhere here. So these structures, as I've mentioned, they are stromatolites, and also very importantly, they are the contributors for the maximum abundance of oxygen in the atmosphere. And in southern Africa, you have stromatolites which are fossilized, stromatolites fossilized from Western Australia, and also Archaean stromatolites of India. So these are all indicators of our past ancestors. And here we see modern day stromatolites, which are basically showing us evidence of how this cyanobacteria blooming on our oceans created these domal features. And they trap the sediments, they bind them and use the sunlight. And this is a basic process of photosynthesis, and with that they deliver oxygen into the atmosphere. And that's how the Earth's atmospheric concentration of oxygen did rise. And with that comes this presentation where we have levels of oxygen shown here, and the Archean time period, which was the time shown here in slices. These are 3.90 billion years, 3.80 billion years, 2.46 billion years. So the record of stromatolites are found from here onwards, 3.5 onwards, and you can see that here 3.5 billion years in this X, Y window of oxygen versus the time is shown. And this is showing that at 3.5 billion years we had no oxygen, as I've mentioned, but roughly around 2.46 we have oxygen jumping into the atmosphere. And these stromatolites are basically the drivers, or the bacteria that were cyanobacteria as an origin. They led to this delivery of oxygen support to the atmosphere at that time. So then we had slow jump, or a very baby jump of oxygen in our atmosphere, and then now we are here where we have 21% of oxygen in our atmosphere. So these are the significance of microbial life in our own lives, because microbes did really shape, and that's how we know them as our own ancestors. They really helped us to be what we are today. So that's what was today in store for us to understand that our Earth, our own Mother Earth, is very special, and we should treat it, love it, and reserve it for more and more research to be done, and what we can have in store for us, because it is with the evolution of our Earth that we have our present day biosphere, geosphere, hydrosphere, and atmosphere. And with this comes the importance of our very own planet Earth, or our own Mother Earth. So thank you for having me today. in this podcast, and I look forward to have many more interactions with the Mexican community.